Now we're moving on to our next chapter on thermodynamics. In chapter 5, we talked about thermochemistry, which is related to the heat or the enthalpy of a reaction during constant process. With entropy, this is a measurement of randomness or disorder in a system / process. So both of these are going to help us to understand if a reaction is going to happen spontaneously or / be thermodynamically favorable. So we'll talk about what that means in the next video. A spontaneous process happens without any outside assistance or any additional energy that needs to be put in. So if a reaction happens spontaneously in one direction, it therefore cannot be spontaneous in the other direction, in the reverse direction. So spontaneous doesn't have to do with being fast. You could have slow reactions that happen spontaneously, and non-spontaneous doesn't mean that it's impossible. It just means that you need to add energy in to make the reaction happen. So some factors that are going to affect whether there is a spontaneous process is going to be temperature and pressure. So for example, ice, so solid water, when the temperature is above 0, the process of melting happens spontaneously. At temperatures below 0, that process will not happen spontaneously. And same thing goes for freezing in the reverse direction. Water will freeze spontaneously below 0, but will not freeze spontaneously above 0. And so you can't go backwards at the same temperature, but you can adjust the temperature in order to get that process to happen. When we think about a spontaneous process, we also have to consider whether it's reversible or irreversible. So a reversible process happens when we have a system and a very tiny change in the system is made so that it can go back and forth between the original state and this new state. So for example, if I have a system and surroundings and they're thermally isothermal, so same temperature, if I increase the temperature of the system by just a small little amount, so that's where that delta T comes in, then the system will give some of its heat to the surroundings. But now the system has a little bit less energy than the surroundings, and so since only a tiny little bit was transferred, then it can go back. So this is a reversible process because the heat is able to flow by just exactly reversing that process. Irreversible processes cannot be undone by reversing the system. So for example, if I have a piston setup here where I have gas on one side and a vacuum in the other side, so nothing's over there. If I remove the partition, so I lift it up, then the gas is going to spread out. It's going to diffuse across the whole container. And if I just put that partition back, that doesn't make the gas go back into the right side. So this is an irreversible process. I have to do work by compressing here, pushing the gas over in order to get it back into the way it was. So any process that is irreversible is also spontaneous. So spontaneous processes are irreversible because you can't reverse them. In order to come back, you have to add work in. So now to entropy. Entropy is a thermodynamic property that relates to the randomness or disorder of a system. It is a state function, just like enthalpy. So we can find the change in enthalpy of a process by finding the final minus the entropy of the initial system. When we have a phase change that happens, which we'll talk about shortly in the next unit, we can find the change in entropy by considering how much heat was either released or absorbed by that process. And in a phase change, which you will see shortly, it is a reversible process at a constant temperature. So when ice is melting at 0 degrees Celsius, it's kind of like at the actual process of going from a solid to a liquid. The temperature is not changing, but we are still adding energy in order to get those molecules to be able to go from fixed position to moving around. So, and they're kind of in this reversible process where they could either go back to the solid state or go into the liquid state. So this is specifically at a constant temperature. So that is for phase change. The second law of thermodynamics says that the entropy of the universe is always going to be increasing when we have a spontaneous process. So, which would mean irreversible. So in that case, the delta S of the universe, which is our system on surroundings, is always going to be greater than 0. For a reversible process to happen, the change in the universe is equal to 0. And so that means that whatever is gained by the system is exactly lost by the surroundings or vice versa. Now we're going to talk about what's happening very briefly with entropy on a molecular level. And this was studied by Boltzmann. So in this case, we're going to think about what are the likely arrangements for molecules to take. So we'll first think about gases. So we know that gases spontaneously expand in order to fill their volume. And if we want to think about how likely or what the probability is for being in a certain area at a given time, or just the likelihood of being in an area, we'll consider the number of microstates. And that is how many ways the system could be arranged. So entropy, we can think about those microstates and relate it to entropy. So the entropy of a system is equal to the Boltzmann constant, K, times the natural log of the amount of ways you can arrange a system. So if I have two containers that are closed, if I'm talking about gases, let's say I have 4 molecules inside A and 0 inside B. When I open the stopcock, we want to think about how likely is it, so how many ways can we arrange the system? So I can arrange, there's only one possible way to get all 4 molecules on one side. There's one way to get all 4 molecules on the other side. I could also put 3 molecules on the left and 1 on the right. And there are 4 ways for that. So basically you're going to say if each of these particles are different, how many ways could I arrange them to get a certain configuration or arrangement? And then we would add up all of those to get the number of ways. And you can see as I increase my number of molecules, there's going to be many more ways that I can orient. So that means that the entropy is going to increase when we have more particles. And that goes along with volume. So if I have a bigger space, then there's more possible positions for my molecules to take up, which means I have a higher number of microstates, or W, which means my entropy is higher. Same thing with temperature. If I have a higher temperature, then I have more kinetic energy. That means that I have more microstates possible because they're going to be moving around a lot more. I'm going to have higher entropy. So I can either increase the amount of molecules or particles, I can increase the volume, or increase the temperature, and all of those would increase the entropy. In these practice problems, we're going to practice calculating the entropy change when we have a phase change. So if we have mercury, it's a liquid at room temperature. Its freezing point is negative 38.9 degrees Celsius. And it has an enthalpy of fusion, which has to do with melting, so how much energy it takes to melt it, is 2.29 kilojoules per mole at that temperature. What is the entropy change of 50 grams of mercury when at normal freezing point? So we're saying that it's going to be freezing. Now this number is to melt. So the opposite of fusion and melting is freezing, so we could change the sign there. So delta H for freezing equals negative 2.29 kilojoules per mole. So if I want to find the delta H, I lied, delta S of this process, I'm going to do the heat of this phase change divided by the temperature. So to find out how much heat I have involved, I'm going to start with my 50 grams of mercury. And I'm going to use the molar mass of mercury to go into moles, since this is in kilojoules per mole. So I have 200.59 grams of mercury in 1 mole. And then I'm going to release 2.29 kilojoules per mole when I freeze it. And then also the units of entropy tend to be in joules per Kelvin. So we want to do one more step actually and get us into joules. So 1,000 joules per kilojoule. So when you calculate all of that, you end up getting negative 571 joules are released when 50 grams of mercury freezes. So now we're going to plug that in. So I'm going to have negative 571 joules divided by my temperature. Now my temperature needs to be in Kelvin, so I'm going to take negative 38.9 degrees Celsius and add 273.15, and I end up getting 234.3 Kelvin. So when I do that calculation, I end up getting negative 2.44 joules per Kelvin. So that means that my entropy went down. So I go from more disordered to more ordered. So let's think about that. When I freeze something, I'm going from a liquid, which is flowy, more arrangements, to a solid, which is more fixed. So that would make sense that I'd have a negative change in entropy. I am decreasing the amount of randomness I have when I freeze something, so that checks out. Okay, now we have boiling point of ethanol is 78.3 Celsius, and its enthalpy of vaporization, so the amount of energy it takes to evaporate a mole of ethanol, is 38.56 kilojoules. What's the change of entropy of the system when 68.3 grams of ethanol condenses? So we're going the opposite direction. So we're not vaporizing, we're doing the opposite. So the delta H of condensation should be negative 38.56 kilojoules per mole. Okay, so at the boiling point. So we're going to do something very similar. We're going to have 68.3 grams of ethanol. And I'm going to use the molar mass of ethanol, which is about 54 grams per mole. And then I'll use my condensation enthalpy. So that is negative 38.56 kilojoules per mole. And then go into joules. So 1 kilojoule is 1,000 joules. So when I have condensed 68.3 grams of ethanol, I release 48,770 joules. So now I'm going to plug it into my delta S equation. Q over T. Q in this case is what we just solved for, so negative 48,770 joules. And now this temperature, I have 78.3 degrees Celsius. So then I will add 273 to that, and I get 351.3 Kelvin. So when I do negative 88770 divided by 351.3, I get that my entropy change for this reaction or this process is negative 138.8 joules per Kelvin. So an even bigger change. When we go from a gas to a liquid, there's an even bigger entropy decrease, than when we have just freezing. The third law of thermodynamics tells us that the entropy of a pure crystalline substance, so a very perfect one, at absolute zero, so 0 Kelvin, is 0. So this would mean that all atoms or molecules in this crystalline substance would be in a perfect structure. There would be only one microstate because that would be the perfect arrangement. There's no other way to arrange it. That is how it is. So that basically tells us that since we can never really, we're still working on approaching that, that is a theoretical value that all entropies are of molecules and atoms are positive. So first we're going to talk about the trends in entropy, and then we're going to actually calculate. Standard molar, this should be entropies, for gases are generally larger than for liquids and solids. But we can get molecules that are larger, so it's not exactly perfect. Because entropies are going to increase with larger molar mass. When I have a larger molar mass, the electrons are able to move around more. I'm going to have more possible microstates within the element and within the compound. Also, when I get more atoms in my formula, my entropy will also increase. And that has to do with being able to arrange it. So there's more flexibility and ways to move the atoms in the chemical bonds around each other. And so you'll have more microstates that way. So here is an image of different phases. So we have water, liquid, and solid water. And you can see that when we have ice, we only have vibrations happening, so we have less microstates. As we have water able to flow, we have the vibrational as well as the rotational motion, and so more ability to move around and more microstates. And then when we have gas, water, vapor, there's basically these molecules all acting independently. There's translation, vibration, and rotation, so we have the largest number of microstates. And we're going to use table 19.1, which gives us the actual value for entropies, molar entropies, for different molecules, atoms at different phases. So first we're going to look at reactions or processes and think about, should the entropy change be positive or negative for this process? So I have a liquid, water, going to a gas. So I'm going from less disorder, so lower entropy, to a higher entropy. So my delta S would be positive in this case because I'm increasing my disorder. Now I have two ions that are in solution, that's the aqueous part, going to a solid, so they're precipitating. So I'm going from more disorder in being able to move around in water to being stuck together in a lattice, so delta S will be negative. Here I have iron and oxygen reacting to form iron oxide. So now for this, we want to think about how many molecules are available and what phases do we have. So here I have 4 solid atoms and 3 gas going into 2 solids. So I have overall more atoms on this side, so more ability to have different microstates, as well as having gas. So I am decreasing entropy when I have this reaction. And here I have nitrogen plus oxygen going to 2NO, And based on, so I have, all of them are gas. So I have a gas molecule and a gas molecule. So 2 gas molecules going to 2 gas molecules. So we actually can't know delta S based on this information. So it's impossible to predict at this point. In this next problem, we're going to figure out which pair has a bigger entropy and then explain. So I have 1 mole of sodium chloride solid or 1 mole of hydrogen chloride gas. So I would predict that hydrogen chloride gas would have a higher one because it is a gas, and molar entropies of gases tend to be higher if they're comparable in molar mass. Now I have 2 moles of HCl and 1 mole of HCl. So because we have more total molecules, we're going to have a higher entropy because there's going to be more possible arrangements for those atoms and molecules. Then I have 1 mole of HCl and 1 mole of argon. So for this, they're both gases. So for this, we're going to want to look at the periodic table. So HCl has a molar mass of 36.5 and argon has a molar mass of 40. Now in this case, argon, so they're pretty close, and we have 2 atoms in here versus 1 atom in here. So their molar masses are really similar, so that's not going to be a huge indicator. But since we have 2 atoms arranged here, then I would predict that that would have a higher arrangement of, or higher entropy because we have more atoms in that compound. Okay, the last thing we're going to do is talk about entropy calculations. So we're going to, just like we did with enthalpy, we're going to look up the standard entropies in the tables, so table 19.1, and be able to calculate. So we can find out the entropy of a reaction by taking the products times their coefficients minus the sum of the reactants by their coefficients, just like how we did before. So you'll be practicing that. We don't have any specific, well, actually we do have a practice problem on the next slide that will practice it. And then we're going to take what we know now about entropy and help us to define Gibbs free energy, which will get us into our last section that we'll talk about next time in the next video. When I have heat that flows into or out of the system, I'm going to have a change in the entropy of the surroundings as well. So when I have that isothermal, so same temperature, constant temperature process, like we did for the phase change, we're going to have the change in entropy of the surroundings equals the heat involved in the surroundings divided by the temperature. Since the heat of the surroundings had to come from the system, that means that it would be the negative heat from the system divided by the temperature. And we know that at constant pressure, heat of the system is equal to the enthalpy of the system. So I can now rewrite that as delta S of the surroundings, so I'm just rewriting this, is equal to the negative enthalpy change of the system divided by the temperature at constant pressure, and technically also temperature. So since our universe, our change in entropy of our universe is equal to the system and the surroundings, and knowing, well, that, for a spontaneous process, the entropy change of this universe has to be a positive value, we're going to now plug in the change in entropy of the surroundings, plug in this equation we did up here. So I'll have the change in entropy of my universe equals the change in entropy of my system. And I'm going to plug in, for delta S surroundings, I'm going to plug in minus delta H system over temperature. So now we have the change in entropy of the universe related to system processes. So now I'm going to multiply everything by negative t. So I'm going to basically get rid of that. Multiply everything by negative t. So when I do that, I get negative t delta S of the universe. So I handle that. Equals negative T, change in entropy of the system, plus delta H of my system. So we end up rewriting this so that way the enthalpy part is up front. So we get negative T delta S of the universe equals enthalpy change of our system minus T delta S of our system. And then we define this whole value right here as Gibbs free energy. And we call it delta G. So now this whole concept is delta G. So we know, well, let me rewrite it. This is our takeaway here. Delta G equals delta H minus T delta S. So we don't need to write system anymore. We can just kind of infer that that's what we're talking about. So for a spontaneous process, we need our entropy of our universe to be positive. So that means this value right here needs to be positive. If I multiply this positive value for a spontaneous process by negative T, then we have a new definition. So when my Gibbs free energy value is negative, I have a spontaneous process. So this is really cool because we're able to combine both what we know about enthalpy and entropy changes in order to figure out if a reaction is going to happen spontaneously. So we're going to explore that in our next video. So practicing our entropy of the system change. So I have nitrogen plus hydrogen goes to ammonia gas. So this is how we form ammonia. And I want to find the delta S. So predicting, let's just predict actually. We have 4 gas molecules going to 2 gas molecules. So based on that, I would predict that my entropy should be negative. So let's calculate. So I would look up in my table, so I'm going to do products minus reactants. So my product is 2 times my change in entropy of ammonia, there's no other product, minus my change in entropy of nitrogen gas, plus 3 times my change in entropy of hydrogen gas. So let's plug in 2. So my entropy of ammonia, we'll go in here and find it, is 192.5 joules per mole Kelvin. And then we'll subtract entropy of nitrogen gas is 191.5 plus 3 times hydrogen's 130.6. So when we do 2 times that value minus this whole value subtracted from that, or added together, I mean, we get our change in entropy of this reaction to be negative 198.3 joules per Kelvin, which is what we predicted. Yay, negative. So that concludes our lesson on entropy. We're going to take these concepts though with us as we finish up our thermo unit.